Good afternoon and welcome to today's HydroCAD webinar. My name is Peter Smart. I'm the developer of HydroCAD and I'll be presenting this afternoon's session. Today we're going to be talking about HydroCAD outlet devices. A principal part of this session will talk about the new outlet controls that have been added in HydroCAD-10, but we're also going to cover the full range of outlet devices that are available so that you can put in context the new devices with the old. There's quite a lot of outlet controls that are available in HydroCAD now, and so we're not going to have a lot of time to deal with each individual one, but this will give you an overview of what's available, make you better prepared to select the appropriate outlet device for modeling a particular situation that you may encounter. Each of the outlet controls that you set up in HydroCAD is typically modeled as an outlet device on a pond. So if we pull out the sample project, which is pre-installed with HydroCAD, if we were to edit a pond there and go to the Outlets tab, that's the place we're going to be talking about during this session today. The Outlets tab can include multiple outlet devices. A pond may have just a single outlet device on one line, or it may have several devices. And at the end of the session, we'll talk about how you might use multiple devices on a pond, either for splitting flows and routing them separately or for building compound outlets such as a riser structure. Those capabilities are all available to you here based on how the different individual basic outlets are configured. So let's start by talking about the different categories of outlets. Basically, the groups we're going to look at today first are going to be weirs in various combinations: sharp crested, broad crested, V and trapezoidal weirs, custom weirs, asymmetrical weirs, and the new dam breach capability, which is essentially a kind of weir. So that's the weir category. We're then going to talk about the orifice outlet. We can have an orifice in a horizontal or vertical orientation, and we want to talk about what each of those means. An orifice can also handle weir flow under low head conditions, which is something we need to look at. And then there are special provisions for modeling grates and flow around the perimeter of a grate. So that will all be in the orifice section of the session. Next, we're going to talk about conduits. Conduits basically are culverts, which have been in HydroCAD since day one, but also the new tube outlet capability, which can also be used to model siphons and even float valves and other devices. So basically those are closed conduits that we'll talk about in a session. And then the final group of outlet devices includes unique things like pumps, which have unique switching capability. We'll also talk about the new constant flow outlet device, which can be used for modeling skimmers and devices of that nature. There's also a special outlet device, which you can use for modeling arbitrary rating curves. And then finally, we'll touch on exfiltration, which is also treated as an outlet device since it's a mechanism by which the discharge of water from a pond is controlled. So that's the rough overview of the outlet device capabilities. So let's go first to a project I've already set up here. To save us a little bit of time, I've got some examples of the different kinds of devices that we will be looking at. Now, in all cases, to set up an outlet device, just to review, you're going to create a pond, usually by dragging it in from the palette. And then you can double-click that pond since it's brand new, or you can right-click and select Edit. And we need to select one of the two pond options, either a detention pond if we're actually going to define storage, or just a catch basin. And a catch basin is a shortcut that has outlet controls on it, but no storage definition, so that the pond node is essentially just assessing the headwater that's present on that outlet device and the flow that it will generate. So at the moment, with the catch basin option selected, we can come up to the Outlets tab, and we can double-click any line here to create any blank line to create a new outlet device, or we can select a line and click the Edit Outlet button. The line we're on here actually doesn't matter. We can have multiple devices anywhere we choose, basically selected for reporting capabilities. So let's click Edit Outlet. And here we get the list of outlet devices that are available. If you are using HydroCAD, an earlier version such as HydroCAD-10 or 8.5, you will see a smaller list. This is the list from HydroCAD-10. If you click the Help button here, It will give you a list of all of the different outlet options, and you can follow through each of these links for a discussion of the parameters, how they're defined, and even a link down at the bottom of that page for the specific calculations. So that's where I'd point you for the most part. If you have further questions about any of the topics today, any specific outlets, go to that outlet device, go to the editing screen, and then follow the help button and the associated links in that topic. And that will give you a lot of additional information. So to start with, our first category are going to be weirs, and these are grouped together at the top of the screen. Let's start by looking at rectangular weirs, which are available in two different flavors. There's a sharp crested rectangular and a broad crested. Let's just look at a sharp crested for a start. And this is a very basic weir modeling scenario. As with all the outlet devices, we have to provide an invert elevation, which is essentially the point at which flow starts to occur. So we're going to specify an invert of 100 feet, which is the crest of the weir. A discharge multiplier with all outlet devices is used if we're modeling several identical devices. So if we had two separate weirs with identical parameters, we could set a discharge multiplier of 2. We can also use that multiplier to adjust the rating curve for a single device. So if we only wanted to discharge 75% of the standard flow through that device, we could use a multiplier of 0.75. The crest length is the horizontal length of the crest at perpendicular to the direction of flow. So if we have a weir that's 20 feet long, we would put 20 in for the crest length. We are dealing with a sharp crested weir in this scenario, so the thickness of the weir doesn't come into play. We're assuming that it is sharp crested, so we're ignoring any broad crested parameters, which we'll talk about in a minute. For a sharp crested weir, normally we have two end contractions indicating that the flow is contracting as it flows over the weir, so the total crest length of 20 feet is actually being adjusted downward slightly based on those end contractions. We can also set it to 1 or even 0 end contractions. So if we have approach walls that suppress those end contractions, if it's fully suppressed, we could set 0 for the end contractions and we could eliminate that adjustment factor. There is also an adjustment factor that's used when calculating the weir coefficient based on the crest height. The crest height is the distance from the approach channel to the crest of the weir. It's not an elevation, it's a linear measurement. It's a height between those two. And this is used to adjust the C factor, the weir discharge coefficient. If you leave the crest height blank, then the software will not make that crest height adjustment, and it will just use the default weir coefficient. And again, for details on any of these things, just click the Help button. It'll take you right to that screen, and then you can go into weir calculations. It'll show you the equation that's being used, and this is the discussion of how the C factor, the discharge coefficient, is adjusted based upon the crest height. So we can fill in all those parameters. We also have one more here, which is a rise. And the rise parameter is available on a number of different outlets. And we would use this if the outlet is in some way capped or limited. So if this were weir flow under lower head conditions, but it was actually an orifice, it was closed off at some height, then we can put the rise. So if there's only 2 feet of open space above the crest, we could put in a rise of 2 feet. And it will basically limit the flow and transition to orifice flow at that point. And again, you'll see that rise parameter on a number of different outlet devices. But generally, you can just leave that rise parameter blank. So we'd fill in the parameters that we need for this outlet device, and then click OK a couple of times, and we've now created a pond which has just that outlet on it. If we double-click that node to perform the calculations, the hydrograph is blank, is empty. It's all 0 because we have no inflow coming to that node at the moment. But we can go to the Discharge tab, and on the Discharge tab we can see the stage discharge relationship for one or however many devices we've created for that pond. So here we're just seeing the textbook flow for a sharp crested rectangular weir going from 100 feet, which is where we put the crest, up to 101. Now, where does the 101 come from? This graph is usually displayed over whatever range we've defined storage. So if we define storage for this pond from 100 to 110, then that's the range over which the report will also display the discharge information. If there's no storage information displayed, as in this case, then the software is just using a distance of 1 foot for the scale. If we wanted to force it to display a larger scale, an interesting trick is we can edit this pond and come to the Advanced tab, and we can put in a flood elevation as another way of forcing a different scale. So if we put in 103 here as a flood elevation, then it now forces a scale of 103. So what I've just done is very handy if you just want to create a stage discharge curve for any given outlet device or combination of devices. You can just set up a zero storage pond, put in your outlets, and then set the flood elevation to define the range over which you want the reports to appear. You can toggle this report to a tabular view either by clicking the table button over on the right, or you can just click the discharge button up top and it will toggle back and forth between a graphical and a tabular view. So the stage discharge curve is very useful. A lot of people will just jump directly and examine the hydrograph when they're doing a pond analysis, and if they have questions or doubts about the results, they may often fail to look at the stage discharge curve, and that's really where you want to go. Your first question is, are the devices behaving the way I expect? Is it producing the expected discharge at a given elevation? Once you know it's doing that, then you can progress and examine the routing calculation, because of course that's adding the additional complexities of the inflow hydrograph with a varying flow plus the storage characteristics of the pond, and of course all of those combine in a sometimes very complex manner. So the stage discharge curve is very useful for verifying the data that you've entered. So that is a sharp crested rectangular weir, and the first sample node that I've already created here has got a sharp crested weir. Actually what I've done here is I've got a couple of different weirs set up. I've set up a sharp crested and a broad crested weir to highlight the comparisons a little bit between the two. The broad crested weir differs from a sharp crested primarily in that the discharge coefficient, the weir coefficient, varies with head. A sharp-crested weir uses a fixed coefficient, whereas with a broad-crested weir, if I edit this one, we have a table in which the coefficient is specified. And in this case, you can see that this coefficient is varying quite a bit from 2.77 up to 3.5, depending on the head. Now, you can enter those coefficients versus head directly if you have that information, but there are also several other ways you can do this in HydroCAD. You can go to this drop-down list for the Crest profile, and these are specific profiles that have been studied. If you click the Help button or go to your HydroCAD Owner's Manual and come down to the link here for Weir Profiles, these are the different profiles that are being referred to. So you can examine this list, and perhaps you can find a spillway cross-section that represents the situation you're trying to model. Another scenario is that you could specify the breadth or thickness of the crest. So if this crest were 3 feet thick, we could put in 3, and it's telling us that the coefficients will be automatically updated as we change the breadth. So the table up above has now been changed, and it's been filled in with Weir coefficients, again based on empirical studies. And if we come back to Help, we can scroll down to the table, and there's a reference here for the exact coefficients that are being used for different breadth weirs. So essentially what we're doing with a broad crested weir is we're allowing the discharge coefficient to vary with head. With some weirs that coefficient may be significant, the variation may be significant. In other cases it may be relatively small. But in most cases I would suggest that you start with a sharp crested weir because the variation in coefficient may not be enough for you to worry about in a particular case. You can always progress to the broad crested weir scenario if you feel that's critical to your particular study. But what tends to happen with a weir on a detention pond is that if you adjust the weir coefficient by even 20 or 30%, there may be a very slight change in the water surface elevation in the pond as it basically seeks out the previous flow. And you can try this, obviously, by making changes on your own. If we were measuring flow rates with this weir, obviously the coefficients would be more critical. But for routing purposes, you'll often find that the model is relatively insensitive to that specific weir coefficient. If in doubt, just give it a try and do a simple sensitivity analysis on your own. So that's sharp-crested and broad-crested rectangular weirs. In this pond, I mentioned I've set up both weirs. And what I've done is I've set them so they have a separate routing. So on each screen, there's this field where we can set the device routing. The sharp-crested weir is routed to primary in this case, which is the default. But then I've gone to the broad-crested weir and I've set the routing to secondary. This simply means that there'll be two separate outflows coming from this pond. So when we look at the report for the pond, we have a primary outflow shown in blue and then a second outflow shown in red. The gray is the total or combined discharge from the two. And on the routing diagram, our node here, our pond, has two separate outflow handles. It has a primary and a secondary. So the flow is being routed in two separate directions, and we would need to make sure we route each of those outflows by dragging it to the appropriate point. If we were to leave an outflow handle sitting on the diagram not routed, then that flow is just disappearing into thin air. So watch for the outflow handles. Generally, there shouldn't be any. They should all be routed to some additional point. Now, coming back to the two weirs, if we go to the Discharge tab, here we can actually see a comparison of the stage discharge curves. The red curve is our broad-crested weir, and the blue is our sharp-crested. And if we switch this, and then the gray is the total combined flow. If we toggle this over to a 2D view, then we can compare more specifically the discharge characteristics for those two devices. So this is another handy capability if you just want to compare device rating curves. You don't actually want to route a hydrograph at this point, then you could set them up as primary and secondary, and that lets you superimpose the two rating curves. So we could adjust the two and see exactly how they behave. So a couple of other tips there that pertain to a range of different outlets. They're not just restricted to the sharp-crested weirs. The other weir capabilities that we have available here, we have a V and trapezoidal weir. And a V and trapezoidal weir, let me just edit this existing case. We are able to specify here a notch angle. That's the primary parameter. This is the included angle, the total included angle between the two sides of the notch. We can also specify a crest length. If the crest length is 0 or blank, then this is treated as a V weir. If we were to specify a crest length, perhaps 1 foot, then it means that we have a 1 foot horizontal crest that's been inserted in between these two sides with a 60-degree included angle. We can also provide a weir coefficient, although the weir coefficient is calculated automatically as we enter the notch angle. If you go into help again, you can find the reference for the calculation of the coefficient. So that's the value that's been calculated for you. You can override it if you wish. And once again, there is a rise parameter which can be used to basically cap the top of the weir. So if this was a V-shaped orifice rather than a weir extending to unlimited height, we could use the rise parameter to indicate the size of that vertical opening. So this is basically just a variation of the sharp-crested weir, but it's allowing us to do V and trapezoidal shapes. The next weir option we have is a custom weir. Now, a custom weir is used for different profiles that we may not be able to fit readily to a rectangular or a trapezoidal shape. And if we edit the case I've already set up, what we've done here is this screen allows us to basically draw the weir. So in the table that we have here, we have over in this column, we're specifying at different heads what the width of the weir is. So in the first line, 0 head and 0 width represents this point down at the bottom. Essentially, that is our invert. So the 100-foot elevation is the elevation for that point right there. So that's at 100 feet and 0 head. Then as we come up in the table, the next point is 2 feet of head, and we've specified that the weir is 4 feet wide. So what we've done is we're coming up 2 feet here, and we've specified that we're 4 feet wide at that point. And then the final value in this table is at 4 feet of head, we're 5 feet wide. So at a total head of 4 feet, we have a width up here of 5 feet overall. So we can use this to define most any kind of custom weir shape, but it has to be symmetrical. That's one of the requirements for this particular outlet device, because this is just the width that we're specifying, and so that's apportioned equally between the two sides. Now, it's also interesting to note that we can do closed shapes with this. So we could actually come up a bit higher to 6 feet, and we could close this off. So we can actually create a closed weir. It's an orifice, essentially. And we can even create a shape which has got multiple openings. And this could be handy if you have something such as a plate used as a diversion structure that may have more than one outlet device in it. So if I can just do this really quickly to give you an example, here we have 2 separate openings, one stacked above the other. And of course, if you put more points in here, you could even simulate or approximate a circular shape or other shape that you may need. So this is a way to provide a single outlet device that has more than one opening in it. It can be a weir or it can be an orifice, either case. So this is quite powerful. This is, again, the custom weir orifice that you'll see on the outlet device list. Now, if you want to model a custom weir shape which is asymmetrical, then we have a new asymmetrical weir option. This is added in HydroCAD-10. It's quite similar when we edit that outlet device to the symmetrical weir, but now rather than defining the width of the weir at different heads, we're actually providing points. Basically, we're describing a cross-section for this channel. So our first line in the table is an offset of 103 feet and a height of 4 feet. So what we're indicating there is that this point here, the first point, is 103 feet over from some reference point, and it's 4 feet up from the bottom of the channel. And the bottom of the channel, that elevation is defined by this invert right here. So at 104 feet total, we're offset 103 from our reference point. So that's defining this first point in our cross-section. The second line in the table has got an offset of 107 feet and a height of 0. So what we're doing with that point is we're coming over here to this point at the bottom, which has got 0 height and an offset of 107. And then we continue that process. We have an offset of 110 and a height of 2 feet, so that comes over and defines this point. And we continue the process for as many points as we need to define our cross-section. So we're no longer limited here to doing a symmetrical cross-section. So if you have a weir which is asymmetrical about a vertical center line, then this lets you draw it. In the analysis, the software breaks this down into a number of rectangular, trapezoidal, and triangular sections, and then uses that to calculate the overall flow through the section. We can specify a weir coefficient here. There's a default that's provided for us, or you can override that value if you want to use something different. So that's the basic process for an asymmetrical weir. Again, the help button will give you a lot more information about how to set that up, including some examples. And stage discharge curve for that is, there's nothing really exciting there. It's just showing you the composite flow for the weir that you've created. Now, the last item in the weir category that we need to look at is a dam breach. And the breach is included here because this is essentially a weir. But unlike the other weirs in HydroCAD, it's a weir whose shape or dimensions, to be more precise, are changing over time. When we define a breach, it's an outlet device. So on the Outlets tab, if we were defining a new outlet, we would come down to the list and we would select dam breach. And it would open up a screen, which I've already got filled in here. But let's just step through this screen for a minute and explain the parameters that are here. The first thing we're doing is providing a top elevation. The top elevation is the top where this breach will start from. So if this were a breach that we're forming in a earthen berm, for example, then the 104 is probably going to be the elevation at the top of the berm. So that's going to be the point where the erosion starts to occur and the breach starts to form and progress, eroding downward through the berm. In this case, we're starting with the top of the berm at 104, and then we're saying that this breach is going to progress down to an elevation of 100. So we're going to get a total of 4 feet, this breach height. 4 feet of erosion is going to occur in this berm as it progresses. The erosion area, the breach area, we're specifying a bottom width here of 3 feet. The breach progress will always maintain that bottom width as it erodes downward. It can also have a notch angle, and this is very much like the trapezoidal weir, which is essentially what we're defining here. This is the total included angle between the two sides. If we leave this as 0, then it's a rectangular breach, so we have vertical sides on both sides of the breach. In all cases, though, that bottom width will remain the same as it progresses. The top will naturally get wider if we've specified an angle. It will get wider at the top, but the bottom will remain at the breach width that we've specified. And then we can specify a weir coefficient. A default is provided, but you can provide a different value if you wish. Now, these parameters on the left here are specifying the physical parameters for the overall breach. Over on the right here, we specify exactly when the breach will start and how long it will take to fully form. We have 2 options for starting. We can specify that the breach will initiate at a given time within the routing, and that's what we've done here. We've specified that it will start at 11 hours. We also could specify a starting elevation. So if we want this breach to automatically initiate when we get to perhaps 104.1 feet, a slight overtopping of our berm, then we could put 104.1 in here to simulate a scenario where that overflow would start to erode and cause the breach. So we have those choices of starting time or elevation. In either case, we would specify the breach time. This is the development time. So from the point that the breach begins to form, this is how long it will take for this full breach height to occur. So the breach will start at the top elevation of 104, and then it will progress down to the bottom elevation of 100, taking exactly 5 hours for that progression to occur. So those are the parameters in the breach screen. If you click the Help button on this, you'll get a very detailed discussion of all the parameters and this little illustration here, which is showing you just how the breach will progress. That we start up top here with a narrow trapezoidal section when we're about 20% progressed, and over time that develops into a larger breach. The horizontal width remains the same, as I've mentioned, and the included angle remains the same, but it means that the top width progresses until we've attained the total dimensions that we've specified on the Weir screen. Down the bottom of the screen, you can follow the link to dam breach calculations, and this will give you a bit more discussion. Now, what we're defining here is, as you can see, a trapezoidal weir whose dimensions are changing over time. So the basic weir equation is the same one that would apply if you defined a trapezoidal weir in HydroCAD. However, its dimensions are actually changing, and that makes it unique amongst all the HydroCAD outlet devices. In order to handle this progression, it means that our stage-discharge relationship is not fixed any longer. It's actually time-dependent. So when we use a broad-crested weir, it's critical that we go to the calculation settings screen, and we have to be using the dynamic storage indication method as our routing procedure. This is like the standard storage indication method, but it's dynamic. That is, we are reevaluating the stage discharge relationship at every point in the routing so that we can adapt to changing conditions such as a breach. And that's why a breach is much more difficult to model than other outlet devices traditionally. You can't do it with a product such as TR20 because it's relying on static rating curves for the outlet devices. So with a timed breach, what I've done in this particular situation is we have a pond which has been pre-filled to a given water surface elevation, and then we've specified exactly when we want the breach to occur. Now, to make this a little easier to understand, if I right-click the graph and go to Report Items and select, I can turn on an elevation curve. And you may want to turn this on all the time. If I then right-click and go to Report Items, Save as Pond Defaults, now it will always give me an elevation curve. So if I close that and reopen, you can see it shows us elevation versus time for all the pond reports. So if we look at this one, flipping to 2D, we can see that we're starting over on the left here at 104 feet. And that's actually just the level that I've preset this pond. So if we go back to Edit on the Advanced tab, there's our starting elevation of 104. So we're basically running a really simple textbook type case where we take a pond, we preset the water surface at 104 feet, and then with our breach outlet, we have specified that the breach will start right here at 11 hours and then progress over a 5-hour time period. So if we come back here to the hydrograph, we can see that our elevation is actually staying constant through this first hour, which this particular model is starting at 10 hours. It's an arbitrary starting time. At 11 hours, the breach initiates. And so we start to see flow initially, this blue discharge curve. And that flow is increasing as the breach progresses. There's no inflow into this pond once again. We're just drawing down the lake level that already exists. And that's what we can see with the gray curve. We can see the water surface elevation in the pond decreasing. Now our breach was set to fully develop over 5 hours, and we can see that here on the graph. We can see that we've actually started at the 11-hour mark, and then we've hit a peak flow here at 16 hours. Exactly 5 hours later is where the breach fully progresses. So our flow is increasing here as the breach increases in size. Then the breach stabilizes, and at this point we have a constant size trapezoidal weir, and now we are just drawing down the level in the pond. So as the water surface elevation drops, the discharge is dropping as well. So that's just a very simple scenario where it's easier to follow the reports and see what's going on. If we go to the Discharge tab, the Discharge tab with a dam breach is going to show us the fully developed condition for that breach. So here we're seeing that when the breach has fully developed down to its lowest elevation of 100 feet, this is what the stage discharge relationship will be. But during the routing, that rating curve is actually changing. It's starting with no discharge through the breach and then progressing to this maximum condition. We can do more complex scenarios. This next example is actually a constant inflow coming into the pond and then a breach that's timed to start at a specific elevation. And this is sort of interesting because we can see here, here's our inflow being generated by a link. It's a constant flow of 20 CFS. That's causing the pond to fill linearly over time. The black elevation curve is increasing. And this comes up until we hit the trigger point for our breach. And let me flip this to a 2D view. And our trigger on this, once again, is set to breach at 104 feet is where it initiates. So what's happening here is the breach is actually initiating when we're at 104 right there. So that's when we start to see some flow through the breach. But the breach is small initially, so the water surface elevation continues to increase in the pond because of this 20 CFS coming in. And then we hit equilibrium, and then the breach is large enough that it's able to discharge all of the inflow plus some of the remaining volume. So you get different shapes here depending on what's going on. It's interesting to note that the peak elevation is attained at some point after the breach trigger. The pond actually went up 0.35 feet from the trigger before we hit equilibrium and started to decline. So there's a lot of different things you can do with a dam breach, and that includes tailwater sensitivity. You might have noticed in this case that, actually I don't have it in this one, but you can route the pond with the breach to another pond or to a reach downstream, which can define a tailwater elevation. And that will be used dynamically. The tailwater at each step in time will affect the discharge through that trapezoidal breach at that moment. And the downstream node, again, can be a reach or a pond, which represents the routing of that flow through the next part of the system, which in turn can influence the breach. And you could even use a link in order to define a constant tailwater elevation. So you could study a breach under that scenario. So there's a lot of different things you can do. Unfortunately, we don't have much time to go into that in more detail, but have a look at that, including the examples that are included with HydroCAD. If you look at the Outlet Examples project, there is a dam breach in there, and you can study that one. Okay, so moving on. We still have a lot to cover. The next general category of outlet devices is grouped as an orifice. And the orifice can be used for a number of different purposes. Here I've got two examples set up for a vertical and a horizontal orifice. Let's edit that vertical orifice. And here on the orifice screen, just a quick run-through of the options that are available to us. If we select opening in a horizontal plane, this means that we have flow through essentially the bottom of the pond or bottom of a tank. So it's a horizontal surface through which we've cut the opening. That's how horizontal and vertical are defined. An opening in a vertical plane would be something like a vertical concrete dam wall that might have an opening cut in it. That would be an opening in a vertical plane. When we select an opening in a horizontal plane, then the software has an option that's by default enabled to use weir flow at low heads. So this means that under low head conditions, when the water is just flowing in over the edges of this weir, the weir flow equation will be applied, and the software will automatically use the limiting case between either weir or orifice flow at each head. So it's not just making one overall assumption. At each head that it evaluates both equations and uses the lesser flow. If we wanted to, we could deselect that and now use pure orifice equation for that condition. Perhaps the only reason you would do that is if you wanted to check the textbook case, but in general you want to have a look at what's happening under those low head conditions. We could also flip to a vertical plane, and when this is partially submerged, it always acts like a weir. So this option for weir flow is selected and grayed out. So we cannot deselect that. If that vertical orifice is partially submerged, it's a weir by definition. So the software transitions from weir flow to orifice flow depending on what the head is. Regardless of the orientation, we can specify the dimensions of the orifice. We can either provide a diameter, or if it's rectangular, then we can put in a width and a length, just the two dimensions for that weir. If it's in a horizontal plane, it doesn't matter which way we enter those dimensions. If it's vertical, then you'll notice this heading changes to height. So we're specifying the width and the height of the opening. Obviously, it's important that we keep those two parameters straight when it's an opening in a vertical plane. We also have a capability here to model a number of identical openings. We could do that either by just increasing the discharge multiplier, but we can also specify the number of rows. So if we wanted to model a grate that consisted of 5 by 5, then when we change rows to a value greater than 1, this multiplier changes, the heading changes to columns. So now we've got a vertical grate with 5 columns across and a total of 5 rows stacked vertically. And in this scenario, we'd need to indicate what the spacing is between those rows. So more realistically, this might be a 2 by 2 individual opening with perhaps 4-inch spacing between the rows, and then we've got 5 rows that are stacked. So there's different ways you can set this up. If we were working in a horizontal plane, there's an additional option for grate dimensions. What this does is it enables this additional box which allows us to specify the dimensions for the outer perimeter of the grate. When we do this, the software can evaluate weir flow through the outside perimeter in addition to looking at the weir flow through the individual openings. So it's basically an orifice within an orifice. It usually only has effect for very low head conditions. So you can try that and see just what the effects may be. And coming back to the examples I've got here, here is an orifice in a vertical plane. And if we flip this to a 2D view and have a close look, we can see that this curve is downward concave initially, and then it flips to concave upwards. What we're seeing is a transition from weir flow when the orifice is just partially submerged to orifice flow once it's fully submerged. So those kinds of behaviors are visible often on the stage discharge curve, which is one of the reasons I urge you to take full advantage of that. We can also look at a horizontal orifice, and this one has got a flow routed through it. Let's just look at the stage discharge curve again. And here we can see, again, an inflection point. We see low flow occurring, concave down, and then quite a change. And I believe one of the things we're doing in this particular outlet is that this is configured to use weir flow at low heads. So there's our curve actually showing us the weir flow behavior. If we edit this and go to the outlets and deselect weir flow at low heads, then when I OK this, you'll see the change in behavior of that curve, particularly this low head behavior. And now you'll notice we have a more rapid increase in discharge because we're looking at the pure orifice equation continuously, regardless of head. So this would not be accurate under that low head condition where we actually want to simulate the weir flow over the edge. So reselecting weir flow, we come back to that more limited case under low head conditions. So the report lets you see those things very easily. And then this is an example showing a grate. I briefly showed you how to set that up. And the stage discharge curve may sometimes show little steps as each of the additional rows of openings shows up if this were vertical. In this case, it's actually a horizontal grate. But if it were a vertical grate, then you'd see that behavior in more detail. For details on all the calculations, once again, just go into the help screen on any of these topics and it'll give you more information. Okay, the next category are conduits, and this includes culverts and tubes. Culverts have been in HydroCAD since day one, and just opening up this example that's got a culvert in it, here we have a rating curve for a culvert. A culvert is looking at a lot of different flow conditions. It's looking at energy loss within the culvert barrel. It's looking at entrance energy losses, frictional losses in the barrel, headwater and tailwater are all being considered in order to combine and produce this curve. If we edit this existing culvert outlet, there's a lot of different options on this screen, but they're fairly straightforward if you take some time to go through them. As with all outlet devices, we have an inlet invert elevation, and we also have an outlet elevation and a length. From those, the software will calculate the slope. The lock buttons here are handy if we want to change some of these parameters. These determine what gets automatically recalculated. So normally, if I change this invert elevation to 101, as I change the invert, you may have noticed it's recalculating the slope of the culvert. But instead, we could lock the slope, and then when we change the inlet, it's recalculating the outlet elevation. So depending on what we lock, it'll recalculate different parameters. If we lock the outlet as well, then I believe it will recalculate the length, in order to match the slope and outlet that we've locked in. There is naturally a Manning's value for any culvert, and you can enter that directly, or you can go to a lookup table and pick from that. We also have the entrance energy loss, the K sub E factor, and you can pick that from a table, as we've done here, or enter a value directly. Then we have the actual culvert geometry or cross-section. The boxes here let you select either a round shape, which is what's displayed. We could also have an elliptical shape, which requires specifying a width, height, and also a top radius. And this can be a little bit tricky. You may have to go into a table book for a particular pipe manufacturer in order to get that information. But we also have in HydroCAD-10 a built-in lookup table, so we could come in here and we could pick the type of pipe, such as reinforced concrete, pick the nominal size, and this will provide the actual dimensions and top and bottom radius for that particular size of pipe. And that's very handy for something like an arch pipe, where the top and bottom radius are actually different. So for those, we can come in and pick the appropriate arch shape that we want to use, and the parameters are all provided automatically. We also have a capability to put internal fill in a pipe. This is used if we have a pipe where we are placing perhaps gravel or concrete inside the invert of the pipe in order to simulate a stream bed condition. And so this takes the overall dimensions that we've provided and then limits it by filling that amount. So what's left is this inner shape right here is the cross-section that we're actually creating once we do that. So there's a lot of good stuff here on the culvert screen. Again, go to the Help button and you'll get more information on how to set that stuff up. Now, closely related to the culvert, we've got it grouped here as a conduit, are tubes. Tubes are a new category in HydroCAD-10, and a tube, as opposed to a culvert where we're dealing with partially full conditions, a tube is assumed to always be flowing full. So this is analyzing a somewhat simpler textbook scenario. And a regular tube is defined by an inlet elevation, and that's simply the invert inlet for the tube, it's very simple, and then an outlet elevation. So that's very much like a pipe with a diameter, but we're now assuming that the tube is flowing full. So we are looking at frictional losses within the tube, specified by the Hayes and Williams coefficient. We're also looking at entrance losses in the tube, defined by an Orifice coefficient. And naturally, we need to know the overall length of the tube when applying the frictional coefficient. So based on those parameters, we can use the Hayes and Williams equation to calculate what the flow will be through that tube. So different approach to culvert flow, and again, it only applies when the tube is flowing full. So we're using this for relatively small tubes. But one of the reasons that this is present in the software is that it enables us to model not just a regular tube, as we've done in this case, but other more complex variations such as a siphon. So let me just go over to the next example here. This is tube flow. Nothing very spectacular about this. What we're actually showing here is the tube when it's only partially submerged. This is a 6-inch diameter, so we're doing a simple linear flow increase while we fully submerge the inlet, and then we're transitioning to the tube flow predicted by Hayes and Williams equation. If we come over here to a siphon scenario, things get a lot more interesting, because now we're modeling here a self-priming siphon. So we're using using the tube flow equation once the flow is initiated. So we're looking at headwater in the pond and even tailwater conditions on this siphon. But we're also allowing the siphon to initiate, to start, and to break at specific elevations. So looking at the description we have for this siphon, we've selected the siphon or float valve, and I'll get to that in a second. We've specified the starting elevation. So this is the elevation at which the siphon would prime, or if it were a float-operated valve, the elevation at which that float would pop and the flow would be initiated. So when we hit 20, we get flow initiation. Then when the water surface elevation drops to 16 feet in this situation, we're breaking the siphon, and we're going to stop discharging. Once we've initiated but have not yet broken, the flow will be determined by the tube equations exactly as if we had selected the regular tube option. So coming back here to this rather interesting graph, we can just take a minute and look at what's going on here. We have a pond, in this case, where we have a constant inflow. So that's this steady green line. This is our inflow hydrograph. It's just a constant flow being generated by a link. And what we're doing is that we're running that into a volume, which is causing this linear increase in elevation as we fill the volume. When we get up to 20 feet, which was the start elevation that we specified for this siphon, the siphon suddenly starts flowing. So rather than zero outflow early on, we suddenly pop up here until we're getting the discharge through the tube. So this flow is based on the water surface elevation in the pond, the tailwater elevation, if there is one, the frictional losses, and the entrance losses. So we immediately start discharging according to that calculation. And so now the pond elevation is decreasing. We're drawing the pond down. And the pond elevation drops until we get down to the break point that we specified, and I believe that was 16 feet. We specified where the siphon will break. So when we get to 16, the siphon flow suddenly stops. If I flip this over to a 2D view, you can see that those points actually correspond. That up the top here, when we hit the 20 is where our flow starts, and then the elevation drops, and when we get down here to 16 is where the siphon breaks. So you can start to model some very interesting and often complex behavior with this, because siphons can trigger several times during a given event, or they might not trigger at all. So if we were to go to this particular, let's go to the inflow that's coming into this pond, and let's change that to 2 CFS coming in. And now you can actually see with 2 CFS, we just turn on once and we stay on. That siphon may never break, depending on the given circumstances. Or it can cycle multiple times. All sorts of different things can happen. Now, the float valve option is basically a siphon, but it's tube flow being operated by a float. And this can be used to model a number of interesting scenarios. There are some commercial products that actually use a float valve to control flow through filters, and that's what's being modeled in this particular situation. So there's a bunch of different options. Basically, it's a self-priming siphon is the behavior that we're modeling, but it might be a float rather than a siphon that's actually activating that mechanism. Okay, so in this category of conduits, we have culverts and tubes. And again, a culvert is considering usually a partially full conduit, where a tube is based on the assumption that we have full flow within the tube, and we're using it to model other scenarios such as self-priming siphons and even float-operated valves. The next and last category of outlet devices has got a range of different kinds of items here. The first of these is a pump. A pump is an active outlet device, obviously. It's an outlet control since it's discharging water from our pond. And I've got a couple of different examples here that I'll go through. The first is simply a pond that's pre-filled with water to a given level. It has no inflow, as you can see. And what we're going to do is we're just drawing down the water in the pond. So here we have zero inflow, the green curve at the bottom, the green line, and we have a pump which is turning on initially, and that is drawing down the water surface elevation in the pond, the gray line, and the discharge rate is decreasing because as the water surface drops, the pump is having to push the water up higher in order to discharge it. So that's a simple discharge scenario from a pre-filled pond. Coming in to look at the description for the pump, a pump is defined primarily by the rating curve that you would provide in this table over on the right. So this can be obtained directly from the manufacturer's information. We also have the capability to load that table in from a file, and there's a couple of sample pump curves that are pre-installed with HydroCAD. So you can do load from file and pull those in if you want to start looking at this in a little more detail. There's a sample pump project which is pre-installed with HydroCAD, so do have a look at that, and it'll give you more details and some examples that are already set up. For any kind of pump, of course, we have to specify the on elevation, that is where it switches on as the water level rises, then where the pump will switch off at some point below that. The water will drop, the float will drop, and the flow will stop. The pump will stop operating. We also have the discharge elevation. So this is the point at which the piping from the pump will discharge, usually into free air at this point, but this can also respond to a tailwater condition. So this might pump into another vessel, and the water level in that vessel could rise above the open end of this pipe or tube causing it to be submerged and increasing the head that is seen by the pump. We can also specify discharge length. If we do that, then we can provide a diameter and again a Hayes and Williams coefficient. So if a length is specified, then we're considering the frictional losses within this discharge tube, and that is combined with the pump rating curve in order to determine the actual discharge that will occur. There's a lot of different interesting behaviors you can model with a pump. I have two more quick examples to show you. This is the pump actually cycling. And in this case, we have a constant inflow of 0.4 CFS coming in, and you can see the water surface elevation rising in the pond. It's hitting the on point for the pump at 105. At that point, the pump comes on. We get flow, which starts to draw the pond down, hence a decreasing flow rate through the pump. We hit the off point, pump shuts off. Then we wait a while as the water surface elevation goes back up, and the pump comes on again. So you can see the actual cycling of the pump. This is deliberately a simplified case where we have just a constant inflow. Because as you start to route storm hydrographs through a pump system, the behavior gets very complex. And it may take a little while to understand exactly what's happening in your model. But here we can see a situation where we have an actual inflow hydrograph in green, water surface elevation going up in the pond, and a pump coming on for the main peak and then cycling on and off in order to handle the lower flows later in the storm. So all of those kinds of interesting and quite complex behaviors can be modeled by using a pump outlet. A couple more outlet devices here to look at. The skimmer is a new outlet device that was added in HydroCAD-10, and this is used for modeling a constant flow outlet. We're talking about essentially a floating skimmer here that might be modeled, and this is an easy way to model a case in which the discharge is essentially constant coming through a given outlet device. And as you can see here, we've got this flat-topped outflow hydrograph from our skimmer. And the skimmer or constant flow outlet is very easy to set up. What you're doing is simply defining the invert elevation where the flow will start, where the skimmer is fully submerged. Or actually, excuse me, this is where the flow starts to go through the skimmer. We also will usually want to define a phase-in depth in many cases. And the phase-in depth is indicating what depth is required to initiate the full design flow through the skimmer. The flow doesn't start instantly when we hit this invert. It usually takes a little bit of depth before we fully submerge the inlet of this device to its rated head and begin the full flow, which is defined here, 1.2 CFS in this case. So if we look at the stage discharge curve, if we look at this closely, we can actually see the initiation happening down here over the phase-in depth before we hit the constant flow at all higher heads. So fairly simple, and you could do a constant flow outlet device first by using a special outlet, but it was a little bit more complex to set up the table. So this makes it much easier, and it provides for that phase-in or initiation of the device. The special outlet device is a more general outlet which lets us define a complete rating curve. So here we can define discharge versus head for the outlet. So we could use this if we had a predefined or pre-calculated rating curve, or perhaps some special kind of weir or other device where we want to plug it in. You used to need to use this for constant flow, but it's now easier to use the separate constant flow outlet device directly. And then the last outlet device we have here is exfiltration. And that's included here because although exfiltration is generally a loss of water into the surrounding ground, it is controlling the flow of water out of a pond, so it's treated as an outlet device. Now we've got a red warning message, and I'm going to come back to that in just a second because that's interesting. But let's just go to the exfiltration outlet. Just to show you briefly, we have a couple of different outlet options, or flow options. We can do a constant flow in CFS. We can specify a velocity, which is applied over the area of the pond with several additional options, or we can specify a hydraulic conductivity in order to apply that conductivity between the pond and a specified groundwater elevation. We do have a separate webinar that was done specifically on exfiltration, and that goes into more detail on these items. So I'd urge you to have a look at that if this is of interest. And of course, there's more information in the help system and our online web pages concerning this. But in this particular scenario, you notice we got a red warning message and this strange behavior here in the curve that we've actually got oscillations. And that can be resolved by going into the exfiltration outlet, and there's a relatively new option down the bottom here, which is the phase-in depth. Normally, if we apply a constant flow, such as this 0.1 CFS, this flow begins very abruptly. It goes from 0 to 1 CFS, and we get a step, which we can see in the hydrograph. This phase-in depth allows us to do a slightly slower initiation. So if we set that phase-in depth at even just 1/100th of a foot, very small, it gives us a slower transition, a soft start and stop, if you like. And that's sufficient in order to dampen those oscillations. So that's the reason for the phase-in depth parameter there on the exfiltration screen. So those are the basic outlet devices in HydroCAD. The last category, last topic I wanted to touch on for today's session is how we might combine those together. We can build things such as riser structures in HydroCAD, and a riser structure could be something that has a vertical barrel, perhaps with openings in the side, flow then coming in over the top, and then a culvert barrel that empties the overall riser. And the procedure for setting these up in HydroCAD is always to start with the last or most downstream device first, and that would be device number 1. So in the case of a typical riser, we would create that final culvert barrel, put that description in, and that would be routed to primary. We would then go on in step 2 and define the side openings and route those through the culvert barrel. And then we could create a top opening and also route that through the culvert. So that's the basic sequence, and that's set up in a couple of example projects. If we go to the Outlet tab here we can see how the routing's been configured. That our first device listed is the culvert barrel routed to primary. Then we have created a side opening with an orifice, and we've routed that to device 1. So what we're doing here is that once the flow goes through the side opening, it goes to device 1 being the culvert barrel. This first column is the device number. So what we're saying is take the flow out of device 1 and run it back here into take the flow out of device 2, route it to device 1, which is back here to the culvert barrel. Then we may have another side opening that we're doing the same with. We're also routing that to device 1, the culvert. And then finally we may get to the top of the riser, and we also route that through the culvert barrel to device 1. So the device routing is very powerful. It lets us combine these devices in order to create more complex structures. And looking at the stage discharge curve, we can see what might happen here with the flow. We initially have 0 flow here at the culvert because we've got a vertical riser, but we start getting flow here at the first side opening. Then we get a little bump of additional discharge at a second opening, more bump at a third, and then finally we hit the top of the riser where the flow spills over. This point of inflection is occurring because the flow is great enough that our culvert barrel at the bottom is actually starting to control. So we see a transition here from weir flow over the top of the riser to culvert flow controlled by the barrel. Again, all outlet devices in HydroCAD can respond to tailwater in addition to the headwater conditions. And when you're doing that, you want to make sure you're using the dynamic storage indication method for routing. This particular scenario, I'm not dealing with tailwater, so the standard storage indication method will work fine. So that is a quick look at all of the outlet devices that are available in HydroCAD. We do have separate sessions that cover some of these devices in more detail, so I'd urge you to have a look at those. And we will have a recording of this session, which will be posted on the website earlier this afternoon. So if you or others want to have a look at that, I hope you will. We have other web sessions coming up in future weeks, which are on our website at HydroCAD.net, and so I certainly urge you to have a look at those. If you have any questions, do contact us at support@HydroCAD.net, and we will be glad to get back to you. Thank you so much for joining us, and I hope we'll see you at a future session. Thanks, and have a great day.